Hi, Sai Jyoti. How are you?
Fine, sir.
Shall we start the class?
Yes, sir. Yes, sir.
Yeah. J- Okay, in 2 or 3 minutes, we'll start the session. Are you able to see the screen, Sai Jyoti?
Yes, sir.
Okay. So let the others join. We will continue our session. Okay. They can join automatically, so no issues in that. If they join late in the class, they will be losing information about GPS. So in the unit 1, so far what we had seen is history of GPS. Is it audible, Hemalata?
Yes, yes, sir.
Yes, sir.
Hello.
Audible, sir.
You're able to see my you're
Yes,
able to
sir.
see my screen.
Yes, sir.
Can you read out the first line and the second line, please? Anyone, either Sai Jyoti
Okay,
or
sir.
Hemalata.
History of the GPS BC4 system. Can I continue, sir?
Okay. So no issues. Thank you. So from this
Okay,
I had
sir.
understood that you're able to see my presentation very well.
Okay,
Okay.
sir.
So shall we proceed?
No one there, no, sir. Only three members are there.
This this session is being recorded. If they are missing the class, they can make a request. Then I'll share them the video such that they can learn. Why you all are waiting for them?
Okay, sir. Continue. Your
This
wish, sir.
every session is being
Continue.
every session is being recorded. So
Yes, sir.
if anybody is missing in any topic or if they're unable to attend the class, video will be shared only at the end of the semester such that they can learn at that time. So why? Because your
Okay.
precious time is being wasted, not mine.
Okay, sir.
So shall we continue? So okay,
Okay, sir.
thank you. So in the previous class we had seen a history of GPS and an evolutionary BC4 system, which was the outline of this presentation which you had seen. So now in today's class we are going to see about NNSS, which we call the Navy Navigation Satellite System or the transit systems. So proceeding on to the NNNS. We had seen this here and concept also in the previous session, where the outbreak of the launch of first artificial satellite, Sputnik, made scientists discover that Doppler shift is being playing an important role in extracting the exact time, position, or location of an individual particle in space or in Earth. The particles could be your asteroids, your celestial bodies, or anything. This we had seen in your last class, which this Hiran used electromagnetic techniques in order to calculate the position of aircrafts or position of any armed forces that was enforced during World War II. So coming to Navy navigation satellite system, this Navy navigation satellite system is the immediate precedent of today's modern positioning system. Google Classroom. So those who are unable to find the link for the GPS classes, go to Google Classroom. You'll be having your meeting ID. Inform them in Google Classroom. The meeting ID is available. Let me check. In Google Classroom, all your meeting IDs available. So go to our class. I think Punashri has joined. So if you go to the Google Classroom, you'll be having global positioning systems, which is meant for Pioneer EC, A, B, C, D section. Google Class code is this, which I'm displaying. In this, you add it using your university student ID. And so here is your link, Google Meet ID link, which will be posted for every classes only in Google Classroom. So this you need to copy and paste it in your Google Meet ID whenever the classes starts for global positioning system. So again, back to the Navy navigation satellite system. This is the immediate predecessor of today's modern positioning system, which we call it as NNNS or transit systems. This system had six satellites which was orbiting at an altitude of about 1,100 kilometers, which was developed by the US military to determine the coordinates of vessels or aircrafts during World War II. They, this was initially developed only for a military usage. So later, this NNNS was eventually authorized for civilian use. That is what we are using today for navigation and surveying. And some of the earlier transit systems, which is called as the NNSS, Navy Navigation Satellite System, was formed by the United States Defense Mapping Agency (DMA) and the United States Coast and Geodetic Survey. They experimented this NNNS system, which showed accuracies of about 1 meter differences for operating over several days. So they positioned a point, they found an object with a mere accuracy of about 1 meter difference in that. So they use the post-process precise FEWMS. So this was the technique being used in the earlier transit experiments, which was performed by US DMAs and US Coast and Geodetic Survey Systems. So how did they do is that they used group of Doppler receivers and they made it in a translocation mode that is used to determine the relative coordinates of points to submeter accuracy. For this, they used the broadcast ephemeris, so where a group of Doppler receivers were placed in translocation modes, determining the relative coordinates of the points to a certain level of accuracy. So this system employed essentially the Doppler-based system that used to track the Sputnik satellite. So when the Sputnik satellite was placed by the Russian in space, what is the travel path of the Sputnik satellite was to be observed, in which latitude, longitude, or altitude this satellite is being traversed. So this was being essentially useful to determine this. So this transit satellites were precisely determined by tracking them, in the sense surveying them at widely spaced fixed sites. They used to fix some points, then they used to find the accurate position of the Sputnik satellite, in which path it is being moving. And navigating with GPS is that navigating is an instantaneous positioning and velocity determination. So what do we call of this navigation is that navigating is determining the position and velocity of the object or the celestial body or whatever we want to find. So which we call as navigating with global positioning systems. So one of the main problems with the transit system was that it was unable to give us accurate results by continuous positioning. For example, if I have a device which is being present in this much latitude and in this much longitude in a place today, if I want to continuously monitor that object's position right from 12 a.m. to 12 p.m., it was very much difficult for the transit system to do that. So that made the evolution of today's GPS. For that, we need to have some constellation. So the constellation, in the sense that deploying at least 4 satellites was a result. And how do we came for that deploying 4 satellites for continuous positioning is what is being given in this satellite constellation. Okay, there are several schemes being proposed which had 24 evenly spaced satellites placed in circular 12 orbits. When you see the clock of our clock, 12-hour clock, so there we had placed 24 evenly spaced satellites in circular fashion such that they are inclined with 550 to equatorial plane, so that we get the desired coverage for at least with a lesser experience. So this was the scheme which was proposed in order to give continuous positioning of an object. So the first point relates that in order to provide a continuous global positioning capability, a scheme should be provided to orbit a sufficient number of satellites to ensure such that at least 4 were always electronically visible, in order to make one is at least 4, in the sense one is used to determine the latitude, one is to determine your longitude, another one is to determine your altitude, and the fourth one collects the information from the latitude, from the longitude, and from the altitude, and it concises and gives us the accurate position of that particular object or for that particular celestial body or for that particular satellite, whichever you want to determine its position. So this was the conclusion and the scheme for that. So in any event in the sense determining the position, any position of any object, this constellation should provide us 24 hours per day, anywhere, any place on the earth or any time. Event in the sense determining the position of the corresponding object or the corresponding material or the corresponding thing which we want to accurately position it. So for that we require minimum 4 satellites which should be in good geometric position. Good geometric position in the sense it should be placed in space where the entire coverage of the earth can be obtained. So that location should be determined appropriately. So that can be determined with the help of our Kepler's law. We will not worry about that. So it is been determined. Next, then the minimum number of satellites available for use should be should be specified for a specified period. So which can be called as surveyors. So this surveyor satellites does this operation. And in fact, an assumption of 100-degree elevation angle, with an 100-degree elevation angle, we can place up to 10 GPS satellites that can be visible. When you want to have a good geometric position. So 100 degrees should be your elevation angle for a satellite, and up to 10 GPS satellites can be fixed in order to provide this good geometric position. And in the next slide, you can see that the GPS, which is can be determined by using this formula. Rho is equal to rho s minus rho r. So what is this rho is that the true distance or the range to each satellite that is to be measured for that particular instance of time is rho. Rho s is the place coordinates relative to the center of the earth. For each and every satellite it differs, place coordinates. Then rho r is the ground receiver defined by its geometric center deployed for that particular time. This is geocentric positioning of that. So the main navigating principle of this GPS satellite is to provide the user to know the capability of what is the position of that. So what is the position exactly can be calculated is done by its three three coordinates. One is latitude, longitude, and altitude. Here, in terms of technically, we call the altitude as elevation. In the previous 2 or 3 points, I told it as latitude, longitude, and altitude. So latitude, longitude, altitude, or elevation, both result is the same. So need not worry about that. So this is being accomplished by a simple recession process using the distances measured to satellites. So you can see that a satellite is being present outside the orbit. I have a geocenter near the Earth. So the distance between the geocenter and the receiver, I write it as rho r. And from the geocenter to the satellite, I write it as rho s. And the difference between these two in magnitudes gives us the distance between the satellite and the receiver by using the simplest method. Next is I need to find the true range rho. How do I find this true range rho? So for this we need to know the velocity of light, which is c. We need to know the value of tau, which is range correction. We need to know the differential rho, which is also range correction. We need to know r value, which is the pseudo range. So what is this pseudo range? What is this true range? So true range is the distance between the points from the receiver to the satellite. Whereas pseudo range are the distances that is being determined virtually. So the virtual distance calculation from the satellite to the point at which we want to determine, we call it as a pseudo ranges. So this slide gives us you about an illustration of how to calculate the pseudo ranges or the virtual distance range between the satellite and the receiver, which we want to determine. So each range defines a sphere, since our Earth is spherical in nature with its center at the satellite. So, the ranges to only 3 satellites could be needed. Why? Because we need to find the latitude, longitude, and altitude. So three range equations are more than enough, which will be obtained from the fourth satellite, which collects all these three range information. So GPS applies a slightly different technique. So where the use of the technique is inexpensive, using a crystal clock which is set approximately to GPS time. The clock of the ground receiver is given with the 2 GPS time, and this offset, which gives us the measured distance to satellites, differs from the 2 range. So if that varies, we can calculate the pseudo ranges virtually. So the R is equal to rho plus del R, sorry, del rho, which is equal to rho plus C sigma. So the definitions and the abbreviations for each and everything is being given. So the velocity of light plays a major role in determining this. So which is c is equal to 3 into 10 power 8 meter per second is the velocity of light. With that we can calculate easily the pseudo range of the GPS. As already said, we require 4 satellites, 4 simultaneously measured pseudo ranges are needed to solve 4 unknown for the 3 components that we require for a positioning of the system. And the solution is being given by a sphere which is tangent to the 4 spheres equations given by pseudo ranges. So the center of the sphere corresponds to the unknown position and its radius equals the range correction. And then we have the range error. So this range error, when determining the accurate positions of the satellite, we need to minimize them. So how do I minimize is that by using the differencing pseudo ranges measured from one visualization to another visualization of satellite positioning. Where the differencing of the pseudo ranges are being measured from one site to 2 or 3 satellites or 2 or different positions of one satellite. So with that we can find the pseudo ranges and we can eliminate our range error. And in the second case, the resulting range difference or the delta range corresponds to the observable in the transit system. So this del rho range correction resulting from the receiver clock error is as same as transit systems. So what happens when we consider the both? So in both the cases, as in transit systems and as in this range correction systems, the data range defines the hyperboloid with its focus placed at 2 satellites or 2 different satellite positions at the geometric location of a receiver. So what does or what did this navigating with GPS gives us? This navigating with GPS, which uses a single receiver, is uh, for determining accuracy of satellite and accuracy of pseudo range measurement and the geometry, which is latitude, longitude, and altitude. So all these for a single receiver are being affected. So this is what the first point is. The accuracy of determining all these things are being affected. The latitude, longitude, and altitude of a satellite, the accuracy in measuring pseudo range, and the accuracy of each satellite position, which leads to some of the errors which we call as systemic errors in the satellite position that eventually leads to satellite clock biasing in pseudo ranges. So how do I eliminate this? How do I accurately measure the accuracy of each satellite position, accuracy of pseudo range measurement, and the geometry of each position? The geometry of each particle is that by using an interferometric approach that lies as a fundamental for GPS surveying. Okay, so that informatic informametric approach that is used to do this is by a measure of satellite geometry with respect to the observing site called as GDOP, geometry dilution of precision. So this geometric dilution of precision is an important concept in understanding the fundamentals of GPS surveying. So all the systemic errors which is being obtained by the satellites, by the clock biases, the pseudo ranges, everything can be eliminated easily by using this dilution of precision. So this geometric approach is inversely proportional to the volume of the body. It depends upon the volume of the material or volume of the object or volume of the satellite or the celestial body, whatever we want to determine its positioning. So this body form is formed by points obtained from the intersection of unit space with vectors pointing from the observing site to the satellites. And we have another slide in navigating with GPS, which is velocity determination. So far, what we are seeing is positioning. Now we are going to see the velocity determination. So there is a huge difference between continuous surveying, as I said earlier. I'll show you the point where we are seeing the navigating with GPS. Positioning, instantaneous positioning, and velocity determination. So far, what we are seeing is completely instantaneous positioning. So now what we are going to see is about velocity determination. So what does this velocity determination mean is that the determination of the instantaneous velocity of a moving vehicle. So far whatever we have seen in the above is only meant for a fixed satellite, a fixed surveying principle, a fixed object which is always stationary in nature, or in surveying of a land body such as these are the examples which are instantaneous positioning: land bodies, water bodies, terrestrial habitats, cultures, desert air surveying, all comes under in the instantaneous. Whereas in the velocity determination, we need to find the velocity of either a moving satellite or a moving truck, moving car, or a moving vehicle, or a moving helicopter, whatever might be. The object which is in moving should its velocity being determined. So this is another aim or goal of navigation. So velocity determination. So how do we achieve this is by using a simple principle of Doppler shift with, of radio signals. So if this principle is understood, it's very much easier in navigating with velocities. So this Doppler shift or Doppler principle in terms of GPS states that due to the relative motion of GPS satellites with respect to a moving vehicle, the frequency of a signal broadcast by the satellites is also shifted when there is when it is received at the vehicle. So I think most of you all are familiar with the Doppler shift. Doppler shift plays an important role So using the Doppler shift principle, we can easily determine the relative motion of a global positioning satellites with respect to a moving vehicle. If the frequency of a signal broadcast by the satellite is shifted when they receive when it is being received at your vehicle. So with this we can find easily the velocity of it. So this Doppler shift is always proportional to the relative radial velocity. And since the radial velocity of satellites is known, the radial velocity of the moving vehicle also can be deduced from the Doppler observable. So for this, how do I determine is that in practice we need to have four Doppler observables in order to solve this three components of vehicle's position, velocity vector, and one frequency pair. So these all can be done. Above all, coming to the conclusion of this navigating GPS is that the GPS provides a 24 hours a day instantaneous global navigation. Navigation in the sense of either surveying or either monitoring or either positioning of any systems. After the navigation, we'll be seeing surveying. Moving on from navigation to surveying comes from the year 1964, so where transit systems were used. These transit systems could not perform very efficiently due to the relative movement of objects either in space or on the earth. So in 1964, I. Smith filed a patent describing a satellite system that could emit time codes and radio waves that is received on Earth as the time delay transmissions, creating hyperbolic lines of positioning. This concept became important in the treatment of GPS observables to compute even precise vectors, which we call it as small variations. Then in 1972, C. Councilman, along with his colleagues in Massachusetts Institute of Technology, reported on the first use of interferometric to track Apollo 16 lunar rover module. So this Apollo 16 lunar rover module was being deployed in Moon for continuous monitoring of information whichever is being recorded. So rover is an object which is being in motion in space or in some other planets or in some other uh, satellites that we deploy for movement and describing the images or finding out the actual informations on that particular satellite. So the principle that they described is in essence the same technique that was later developed as the first geodetic GPS receiver and corresponding to differencing pseudo ranges measured from two receivers to one satellite. So from two receivers we came to one satellite. So the present use of GPS carrier phase made to move on to millimeter wave measurements, which was being dated back by MIT group, saying Massachusetts Institute of Technology, which used a very long baseline interferometry that was performed between 1976 and 1978, where they proved that this short lines or the millimeter waves was accurable using this interferometric technique. In 1978, the miniature interferometer terminals for Earth surveying were proposed which was used for precise surveying. So a small amount of surveying objects, lands, or satellites or celestial bodies, which was developed in 1978. So miniature interferometer terminals for Earth surveying, surveying the land resources. So this concept was further included with the navigation system. So this was called as NavStar, NAVSTAR, navigation system with timing and ranging, navigation and surveying together, navigation system with timing and ranging, which we call as NavStar. Also, the codeless technique that is important in developing this high frequencies were also described for the first time. Codeless techniques was being used in this NavStar. So what were the observational techniques for this is that in order to achieve high accuracy, GPS surveying implied precise measurement of vectors. Precise in the sense small variations of measurements between two or more GPS receivers. These techniques were both receivers having static in position. The GPS receivers never moved at all, they were static in nature, which we call it as fixed in positioning. The positions of these two GPS receivers were standstill, means that they never moved at all. So with that, they found high accuracies. Next, this static method required more hours of observation. If I want to record static positions details, it took many more hours for observing that, so which was used in your earlier GPSs. And the second technique is that where when we have two or more GPS receivers, if I want to find the precise measurement of the vectors between them, I can make one receiver to be as fixed and another receiver to be in moving. So this type of technique is called as kinematic surveying. One is static surveying, where both the receivers remain in fixed in position. Another technique is that kinematic technique, where one receiver remains fixed and the another receiver tends to move. So with that, observation of the exact position of them can be determined. So the further development in this was done by B. Raimondi in 1986. He demonstrated that sub-centimeter vector accuracies could be obtained by a pair of GPS surveying instruments with a little, just a little, not so much, with a little knowledge of a few seconds of data surveying that developed to another technique called pseudo-kinematic technique. So this pseudo-kinematic technique is a technique that used a little information or a few collection of data with the existing method, and they developed another technique called pseudo-kinematic technique. So in this technique, a pair of receivers occupies a pair of points for two brief periods that are separated in time. This method denoted intermittent static, snapshot static, or reoccupation. That is much more that is giving much more accuracy comparable to static methods. So this was being developed in 1986. And another is that how this data are being processed. How do we process the data using the observed? So from the observed data, the data can be processed in two conceptual ways. One is the first one, relative positioning. Second one, differential positioning. So what is this relative positioning is that it is a technique where all the data, simultaneously observed data, are processed, and the result is instantaneously obtained relatively. So next one is differential positioning. In this differential positioning system, where we use a receiver to be fixed at a known position and another receiver which you are going to move in an unknown position. So comparing the computed ranges with the measured pseudo ranges, the reference site can transmit corrections to a roving receiver to improve its measured pseudo ranges. These techniques provide instantaneous positioning, and this can be used mainly in kinematic surveys. So kinematic surveys is what where one receiver will be fixed and other receiver will be in motion or it will be in moving. So what are the hardware developments for this surveying is that we need to use some coding systems that was developed by US military named Macrometer Intermetric Surveyor, and the former name of that is US Federal Geodetic Control Committee or GCC. So they had given this hardware development systems. If a GPS is there for developing for doing a surveying, they should consist all these things. So one is CA codes, course or acquisition, and the P codes, which is precision codes. They should be basically coded such that their signals are being modulated on two carrier signals that is to be broadcasted by a GPS satellite. As an EC engineer, most of them are familiar with the term modulation, I think so. So after the code correlation, as well as the coding techniques, these codes from the carrier can be reconstructed and it can be measured easily. So the brand names mentioned in this section are only for historical purposes. They are only to represent their history, not any specific technical systems. So the first one is your interferometric technology that we I had said in just 2 or 3 slides before. Interferometric technology, which is used only for codeless pseudo ranging, developed by Jet Propulsion Laboratory. And another technology which was used as a hardware development is satellite emission range infrared earth surveying series technique, which was improved for commercial geodetic applications. And the VLBI, Informametric Research, which was using a portable codeless GPS receivers that could measure shortable baselines to millimeter technology. So this VLBAI, which is your very long baseline informametric, is an advancement to your informametric technology that we had seen in the earlier slides. So where this baselines can range from can give us an accuracy of just 1 or 2, 3 millimeters of accuracies can be given, which has a long baselines of 1 part per million, 1 part per million ppms, 1 ppm. Okay. So this is the trademark the hardware developments. Later, the DMA, in cooperation with the US Geodetic Surveying System, UGGS, and the US National Geodetic Survey, all combined together and formulated and hardware systems from different agencies. So these agencies used dual frequency correlating receivers, precise surveying, point positioning, and most probably the Texas was the company that was given the contract to produce receivers, especially for GPS surveying. Later, the trade name changed to TI4100. Then the NGS the geodesists, the GOD and B Remori developed a software to process the carrier phase data in such that this could be easily adaptable by the Massachusetts Institute of Technology, that is the Informatically groups. Later, this TI4100 was significantly different from the macrometers. So this came to a standstill, and which used a dual frequency receiver with P code to track maximum four satellites. I, I think I had left a space between off and four, so it should be off comma space. So tracking of maximum four satellites with the original macrometer having a track mounted up to six receivers. So for now to determine a single position, a minimum of four up to six satellites were necessary for this TI4100 surveying hardware. There were also some significant logistic differences in performing surveys using these two pioneer instruments, the Texas and the Informative. And I have another slide on another presentation on the hardware development, where they used broadcast ephemeris and the timing signals from GPS satellites such that they could operate independently. So the macrometers that the ephemeris have for each day's tracking being generated for every observing sessions. In 1985, the manufacturers started to produce C-bar A code receivers that measured the output of the carrier phase, and a trademark name during this 1985 was given as Trimble 4000S, which used only C-bar A code receivers. This receiver was later developed such that it can be connected to an external device, example a laptop computer or a PC, and so on. And this Trimble 4000S series were the host of manufacturers for this. They sold these receivers without processing any software information, and soon the company retained the services who produced appropriate vector computation software, which set the standard for future software developments. Today's GPS receivers include all the features of the earlier models, and additionally, they have expanded capabilities as in modern day. So as far as this major portions of the receivers produced today We'll have an duplication work of TA course acquisition code single frequency type. And in order to have a good precise geodetic work, the more expensive dual frequency receivers are a standard in terms of hardware. And in the evolution, not only hardware plays a major role, we have an software also which can pre-process the data. So the software developments of GPS surveying has largely parallelized the development of hardware also. So NGS was one of the primary organization in developing independent processing softwares. This produced processing softwares that the macrometer phase measurements and the precise epidemics produced by the United States Naval Surface Warfare Center. So United States had a Naval Surface Warfare Center which was being governed by this NGS such that measurements can be done accurately. Okay. So the other macrometer systems used or had to apply processing software which was developed by macrometer manufacturer that required the use of specially formatted ephemeris produced by them. So which was later adopted by the TI-4000 format data. So the original software developed by this both NGS and the manufacturers computed individual vectors one at a time, where these vectors were combined in a network or a geometric figure corresponding to all the points that were determined using least square adjustment programs. The NGS and the macrometer manufacturer eventually they developed a processing software often called as session in order to simultaneously determine the vectors being observed over a given period of time. Then came the next, a second set of generation multi-baseline software that included the ability to determine the corrections in satellite orbits, and this was referred as orbital relaxation software, developed at Brentse Astronomical Institute by the G. Brutus Group. Next is the ephemeris service being provided by the surveying with GPS. Since the first GPS surveys performed in the late 1982s using macrometers, they were depending upon the orbital data derived from a private tracking network. Later, this broadcast ephemeris were used to supplement this private tracking data. So initially, they had used TI-4100 receiver that obtained the ephemeris broadcast by the satellites such that processing programs could use this ephemeris to process vectors. The NSWC originally processed the military ephemeris, obtaining precise, which is your small, pre-processed ephemeris, which were turned over to NGS for limited distribution to the public. Nowadays, various organizations around the world provide satellite tracking data from points that are referenced to a global data. So the tracking solution stations collect these code ranges, phase data for both frequencies for all these satellites. They collect all this information. So on a daily basis, these data are being processed and are being archived also. Once they are being processed, they are being archived to a place. So more precisely to speak about ephemeris, is that they are available to each and every public only upon a request. If somebody asks the positioning of a particular vehicle, particular object in space, particular celestial body, once a request is being made to the NSWC, they give the data within a few days to civilians. So now, what is this GPS meant for? What is this GPS meant for? So what does it does? This global positioning system was developed to replace the transit systems or the NNSS system because of the two major shortcomings in the transit. So one is it had larger time gaps in coverage. Second is that it was having lower navigation accuracy. So 2 points which came to the evolution or to the uh, scenario of global positioning is that one is larger time gap in coverage within the transit system and the low navigation accuracy. Low navigation accuracy in the transit system, which came to the evolution of global positioning system. So what happened in the larger time gaps in coverage is that a satellite nominally when passed goes overhead every 90 minutes and the users had to interpolate their position between fixes or passes, fixed position or the moving position. So for every 90 minutes it was very difficult in the transit system. And the navigation was also very lower in order to measure its relative position. So since the accuracy was very low, they shifted to global positioning. So in contrast to all this, what is GPS? Is that GPS can answer all these questions. What time, what position, with what velocity is it? What time, what position, and with what velocity is it? Quickly, accurately, and most important thing, inexpensively, anywhere on the globe at any time. So this is the desire of GPS. What time, what position, and with what velocity is it anywhere on the globe at any point. You can find it. So this is what GPS is. So any queries till this, such that I can proceed further? I'll go back to the how many are present. Let me check it in the meeting. Oh wow, 28 people had joined. Very good. When the session started, we were only three or four. Okay. Most probably everyone had joined using their university ID. Very good. And I inform you all that everyone should get added in the Google Classroom using only your registered university ID. I'll show you who all are being added. If you are not added, kindly join in this presentation. I'll show you. So every session, every session ID will be created for every meeting. So that will be shared only in Google Classroom. You can see that. I'll show the persons those who are already added. I'll read out them. If your name is not coming, you need to get added. Jayant is there, Kirti is there, Nikhil Chaudhary, Venkat, that's not see your name, right? Chakkavira Venkat, Hemalata, Ashok Naidu, Abhiram Sharma, Ajay, Arvind, Purnashri, Vishnu, Sivasai, Venkat Pavan, Akhil, Sridevi, Raghunath Reddy, Rakesh, Satish Kumar, Monica, I suppose Monica, Krishna, Sundar, Lalita, Balaji, Bharat, Lokesh Rahul, Madhav Reddy, Nagarajesh. So these are the persons who have been already added. If any of your friends is not available, kindly inform them to get into this Google Classroom using this code. I'll show you the code. This is the code for GPS Global Positioning System class code. Kindly join with this Google Class code such that all the informations will be passed on only in this Google Classroom. The meeting IDs, the materials or the posts or any information on that will be done only in Google Classroom. And those who haven't joined, join with only your university ID. Join only with your university student ID. Do not join with your personal email IDs. So any doubts till this? What is the necessary for a global positioning system? The answer to the global positioning system is that what time, what position, and what velocity the object is in can be determined easily, quickly, accurately, and without any much more expenses anywhere on the globe at any time. If someone is having any doubt, shall we proceed? Available? Partha, shall we proceed? Partha, yes, Partha is connecting his microphone.
Sir,
How are you, Patas?
sir, आगे sir ब्रह्मांड को ना
Shall we proceed? Okay, shall we proceed?
yes sir
Because already 1 day they had declared a leave for you all for GPS, which we had on Saturday. Okay. Next topic is about Navstar, navigation system with timing and ranging navigation system with timing and ranging. So the Joint Program Office was the responsible part was the responsible office for the Joint Program Office was the responsible office for compiling this NumStar. So this JPO was being controlled by the US DoD, Department of Defense, which established, developed, tested, acquired, and deployed a space with bone positioning systems. This positioning system was conceived as a ranging system from known positions of satellite in space, positions on land, sea, or in space. This Navstar positioning system the name of the ranging of known positions of satellites its own transmission time such that the received signal transit period can be measured with the synchronized receivers. Moreover, the objectives of the GPS were instantaneous determination of position and velocity, instantaneous determination of position and velocity, which we called as navigation, and the precise coordination of time, which we called as time transfer. Coming to the next is the GLONASS, Global Navigation Satellite System. GLONASS is an Russian equivalent of GPS, which was evolved in 1990s. So this GLONASS, Global Navigation Satellite System, differed in terms of control segment, space segment, and signal structure, remaining all were equivalent to GPS. The difference was only in the controlling, spacing, and signal structuring. Since the Russians and the US were having equal power in those years or those days, such that they can become superpowers of the world. In order to have both control over military, they operated like this. So the GLONASS was operated by the Russian military, space forces, MSFs. They applied different frames as well as different time references, which were based on a Russian parameter of the Earth PE90 system and the reference time UTC, which was maintained by UTC refers to Universal Time Codes, which was maintained at the Russian Institute of Meteorology for Time and Space. Unlike the GPS, the reference of GLONASS is not continuous, since some of the leap seconds were inserted, where but the space segments were similar, which had 24 satellites. The GLONASS also had 24 satellites, equally spaced in three orbital planes with 64.8-degree nominal inclination. Whereas in the navigation of GPS, we had used 110-degree equatorial to Earth. So the nearly circular orbits with altitudes was about 19,100 kilometer and a period of approximately 11.25 hours was the altitude and time period calculation, which is more or less similar to your GPS. The higher inclination of GLONASS orbits increased its accuracy and availability at higher latitudes. So the latitudes at higher accuracies was being determined when the inclination of GLONASS orbits were increased. A substantial difference between the two systems occurs only in the signaling structures. signaling structures made an major difference between the GLONASS and the GPS. So what does this GLONASS used is that they used CDMA, code division multiplexing accessing, where every satellite transmitted the same two carriers modulated by pseudo-random noise codes, specifically assigned to each satellite. GPS used this, whereas GLONASS used FDMA, frequency division multiple access schemes, where each satellite had two individual carrier frequencies were assigned to them. So how to calculate the pseudo-random codes for both the systems were common. However, for both the satellites, the pseudo-random PRN codes were calculated simultaneously, where the transmission structures used by the GPS were CDMA, whereas for GLONASS it was FDMA. So here I am listing you and frequency, carrier frequency, which is given as FL1, FL2 for these satellites. Considering J is the carrier number assigned to a specific satellite, the FL1 was calculated in GPS as 1602 megahertz plus 565 megahertz. And the L2 frequency was calculated as 1246,246 megahertz plus the frequency of the specific satellite, sorry, number of carriers of the specific satellite into 0.4375 megahertz. So always the ratio laid in between 9 for FL1 and 7 for FL2, so which is 9 bar 7. The next is the GLONASS to be continued. Same carrier number can be used for certain antipodal satellites. Antipodal satellites refers that the positioning of a satellite virtually with another satellite. Yeah, continue. As far as the as far as GPS are concerned, two codes can be modulated onto the carriers. One is the free accessible post acquisition code with a chip rate of 0.511 megahertz, having a time period of 1 milliseconds on one L1 frequency. Another with a P code or the precision code with a chip rate of 5.113 megahertz with a time period of 1 seconds on both the carriers L1 and L2. Whereas this GPS did not have any provision for encryption. So this GLONASS had a provision for encryption. The chipping rates for GLONASS were approximately 2 times lower than the corresponding values of GPS. If I find the chipping rate of a GPS and if I compare with the chipping rate of GLONASS, GLONASS were approximately 2 times lower than that. So this had an advantage of GPS systems. Now the structure of the navigation message became different from the GPS. Every half an hour, the satellites can transmit their geocentric positioning, velocity, and acceleration vectors. So the position vector should be interpolated by the user for observing this approach points. So which is about the GLONASS introduced by the Russians, Global Navigation Satellite Systems. This is the Russian equivalent of GPS. Next comes the GNSS. The advantages of GPS and the advantages of GLONASS were combined together and integrated with the geostationary satellites, which came as Global Navigation System (GNSS). So examples for such civilizations were the the European Geostationary Navigation Overlay Service (EGNOS) and the Japanese Augmentation System (MSAS), based upon their multifunctional transportation satellites. They merged them to a single system called Global Navigation Satellite Services. So the transition from the military systems to a system under complete civil control was being evaluated in this Galileo project, which was a contribution by the European side. American side, they had contributed with the GPS. GLONASS was contributed by the Russian side, and the augmentation of this with the European named Galileo project led to this GNSS also. So here is a frequency allocation of the designed band L5 band, L2 band, and L1 band. Its bandwidth, how it was used in allocation for L5 as GPS, and if it is if it is represented as L, it represents GPS. If it is represented as E, it represents Galileo project. If it is given as G, it represents your GLONASS project. So keep in remembrance these three. L represents GPS, E represents Galileo European system, G represents the GLONASS system. So the bandwidth between 1164 to 1188 were allocated for L5, 1188 to 1212, sorry, 1214 was given for E5, 12152 1239 was given for L2, 1237 to 1260 was given for G2, 1254 to 1258 was given for E4, 1260 to 1300 was given for E6, 1559 to 1560 was given for E2, 1563 to 1587 was given for L1, 1587 to 1597 was given 91 was given for E1, narrow band, and 1593 to 1610 was given for G1. Next was the GNSS, the Loran C integration. The Loran C integration was an Russian counterpart of Chaika, which is a terrestrial radio navigation system where a number of transmissions transmit high power pulses in lower frequency. That is, the frequency is from 90 to 110 kilohertz band. Loran C integration of GNSS. The broadcasting stations were organized into chains with one master station, which will control all the other 2 to 5 secondary stations. Then there were cesium clocks of the reference stations that synchronized with a few tens of nanoseconds. Within a few to 10 nanoseconds, we can get the observations of positioning, since the number of stations transmitted at higher power with lower frequencies. Then there were Loran C receivers being equipped with low-cost clocks to measure the signal runtime from the reference stations. They used two clocks to be involved. One is as a reference and one is at a roving. Rover in the sense it is in motion. And the final observables were measured as pseudo ranges. Thus, the positioning of this Loran C exactly resembles GPS positioning, which had a larger coverage area, improved availability, and external integrity information. Larger coverage as compared to GPS, improved availability within GPS and external integrity information of GPS. So with this, I would like to show you the references. I'll show you the references. Go through these references. These are the textbooks which are being referred. For this presentation, mainly I had referred this second V. Hoffman, Manual of Richard and J. Collins, GPS Theory and Practice. This is the prescribed textbook and book also for global positioning system. So any queries, I'll give you 5 to 10 minutes. After that, we'll have it. I'll take the attendance. I'll give you 5 to 10 minutes for discussing among yourself also. You can have a discussion within yourself. Have a discussion.